All right. So as I mentioned, you now have mastered all of the tools that physicists use, conceptual tools. Okay. You've barely learned any mathematical tools, but that's higher level. If you continue on with physics, for example, say you take 110, 120, and 211. That covers the first 2 years of physics. And you effectively learn all of the concepts that you need to know. If you're a physics major, which I was, when you're your junior and senior level courses, you basically relearn everything. But you relearn it with stronger mathematical tools. There's a lot of things you don't know right now. You don't know differential equations, technically. You don't know linear algebra, technically. You don't know a lot of series and sequences stuff, technically. Okay, and so junior and senior level physics is fun because you've hopefully learned the concepts, and now you just use power tools to solve your problems. Power tools being the mathematics, and then when you go to graduate school, it's the same deal, except they're just meaner to you. That's pretty much it. All right. Okay, so the next several chapters is applications. And you're going to see everything here. Kinematics, forces, energy, momentum, it's all mixed together. Those are all the tools that we use. And so what will be the most challenging thing for you, possibly, is trying to figure out which tools are the right tools. And that's a big part of learning physics, is knowing that you have all the tools at your disposal, and it's important to know which tools are the correct tools. How do you learn that? Experience. It's just experience. You have to just try a lot, and you have to mess up a lot, and you try more, and you mess up more, and you try more, and then eventually it sinks in. It's a lot of trial and error, which is fine, because that's true of everything. You screw things up, you get better at stuff. Okay, I gotta get to the lecture here, or I'm gonna be ranted for 2 hours. All right, now up to this point, we have discussed what we call the particle model of physics. And the important aspect of the particle model is that we did not previously care that objects have shape nor size. We never cared about that. Now we do. So the next few chapters will now explore how we have to consider size and shape of an object in order to solve our problems. It was a simplification that we made previously. Now that we're better at it, we can relax some of the simplifications and create more complicated problems. However, we don't go all the way with it. We still have some simplifications. And one of those simplifications is what is known as the rigid body model. Our objects now have shape and size, but there's still some things we're going to assume about them. We will assume that they are rigid bodies. What does that mean? They do not bend. Their shape and size is not altered at any point in the process of solving our problems. However, there is an additional layer that you will consider if you move on in physics, if you move on in engineering. You learn about things called stress and strain. You learn about Young modulus. You learn about compressions, and you can start to work out if you don't have rigid bodies. We do not do that in Physics 110. All right. So, if our objects are no longer particles, then they have an additional dimension of motion to them that we will consider. Previously, all the motion that we considered was what can be described as translational motion. The object is a point and it moves around. If now we consider that objects have shape and size, we have an additional layer of motion that we need to consider. That in addition to the objects moving around from one location to the next, they now can rotate. And that's a different treatment. Okay, so let me give you an example of this. Say I have my I got my switch here because I'm waiting for noon for my turnip prices. I wasn't happy with the morning turnip prices. But anyway, if I have my switch here, right? I could throw this. Oh, actually, I'm not going to do this with my switch. That's kind of good. All right, I'm going to do this with my calculator, right? So you could throw this calculator up into the air. And say I did that and I didn't produce any rotations. It would simply go up and come down, and that's all particle model stuff. But what if I threw it up at the same speed, but as I did that, I kind of tapped it on the right-hand side here, and I made it, rotate around like this. This motion here, just throwing it up and having it come right back down, is very different than if I take my object and I spin. Oh, geez. And I spin it that's very different. In fact, if I spin it as I throw it up, I'm actually going to impart a lot more energy into this object. So rotation becomes really, really important in these problems here. All right. So we're going to combine the two together, and that's a really big part of solving our problems here. Okay. So what I want to do first, though, is I want to go back and I want to sort of remind you about a lot of the details related to circular motion that we talked about before, and I'm going to add some details as we move on here. So one of the things that hopefully you remember is the concept of angular velocity. And so that's given right here. Omega is angular velocity. It is given in terms of radians per second. And it's a way to express how objects can rotate that is independent of their size. If you have a disk, like you see in the picture here, all parts of the disk, if the disk rotates uniformly, have the same value of omega. They have different values of velocity, though, and you see that right here. This VT, this is the translational velocity of a part of the disk. And if you're closer in, that's not as great, and if you're further away, it's much larger. Okay, and that's still important, don't get me wrong, but omega is the rotational equivalent velocity, and it's going to serve a greater purpose than just standard V. Okay, I didn't talk too much about the next idea before, but we also have what we call the angular acceleration. The reason I didn't talk about that before is because our previous discussions were devoted entirely to uniform circular motion. And in a uniform circular motion, your alpha is 0, but now it will not be 0. We are going to allow things to rotate and speed up and slow down. And the units of that are what you might expect as radians per second squared. Okay. Again, the reason why we develop these ideas is because they are independent of the size of the object. If this disk rotates and, say, speeds up, for example, then at any given point in time, any location on the disk has the same omega and alpha. Okay, moving right along. All right, so if there is an alpha, we refer to this as non-uniform circular motion. Okay, so as you see in the figures here, all right, we have this initial condition where we start off at rest at t equals 0, and we have an angular acceleration of 2 rads per second squared. That means after a second, our disk is going to accelerate, and then after a second, we are now traveling at 2 rads per second. And after 2 seconds, we're 4 rads per second, and so on. It just basically describes how much we're speeding up or slowing down rotation. Now, the thing I really want to emphasize about these concepts is there is a huge amount of analogies between translational and rotational motion. The alpha is the same as the A, and the omega is really the same as the V. The relationship between the two is simply a radius, and you'll see that in a moment here. Okay. Now we do have conventions. Because when we had translational motion, it was pretty, we usually said, oh, if you're to the left, it's negative, and if you're to the right, it's positive, and if you're going up, it's positive, and down is negative. That's a standard convention for things. When it comes to rotation, we have a more standard convention. And this is really not something you ever want to mess with. When we did the problems before, like translational problems, sometimes it was okay to say downward is positive. Because, maybe you have an object fallen and everything is downward. So it's just easier mathematically to say, well, I'll make down positive. You shouldn't really do that for rotation now. Generally speaking, if you have counterclockwise motion, that is what we call positive. So omega going counterclockwise is positive, and alpha going counterclockwise is positive. And if you go clockwise, we call that negative. Okay, and the same rules apply to considering speeding up and slowing down. So, for example, if you look at this situation right, here's what I want to highlight. If alpha is positive, alpha is positive if omega is decreasing and omega is clockwise. Okay. So when we say decreasing and increasing, that is speeding up and slowing down. So the same thing does apply. Alpha is positive, and if omega is clockwise, that means negative. So you have opposite signs for your acceleration and your angular velocity, and that means slowing down. If you look at the statement up here, alpha is positive, omega is counterclockwise. That means omega. And that means you will be speeding up. And the situations down here give similar things. So I really can't emphasize enough how much there is a translation, a direct translation between translational motion. I shouldn't use that word, I guess. Translational motion and rotational motion. And what hopefully you will find is that a lot of these problems are not incredibly challenging because you really already know how to do them, assuming you learn kinematics. But if you didn't, you got another chance now. So, all right, got a question for you. Again, don't chime in with the chat here. Just think about it. What do we see here? We have a fan that is spinning clockwise. It is slowing down. Okay. So the first thing you want to do in this problem is consider omega. Then you can consider alpha. The answer here is, you ready for this? C. Now, here's the logic here. Our rotation is clockwise. That means omega is negative. A and B is wrong. A and B are wrong. We're slowing down. Okay? By definition, slowing down means that your omega and your alpha are opposite signs. So if we establish that omega is negative and we slow down, alpha must be positive. And I recommend that's the way you think about it. I mean, if you consider this, if you allow the alpha to act as long as it possibly could, the fan would slow down, it would stop, and it would start to spin counterclockwise. Okay, great. All right, so you know something already, right? Here's what you know. You remember these. Equations 1, 2, and 3 of kinematics. You've already learned them. You already know them. And if you look at the equations on the left, guess what? They look completely identical. Instead of V's, you have omegas. Instead of S's, distance, you have thetas. Instead of A's, you have alpha. And guess what? You know how you get from the right to the left? Oh, I'm having too much fun right now. This is fun. I'm loving this stuff. You divide. Oh, capital D. You divide by r. That's it. If you divide every single one of your well, you're just basically dividing all three equations by r. And that's how you convert here. Because what you might remember, and unfortunately, oh, you know what? Shoot. I have not figured out, because I'm a little lazy, not figure out how to do special symbols in here. But anyway, the relationships for these quantities are the following here. S divided by r is theta. V divided by r is omega. And A divided by r is alpha. So there's a good reason why these equations look equivalent, because the physics is the same. It's completely the same. It's just you have to modify this by r. And so some of the other things that we learned about before, the stuff that you see here, alpha, it's the slope of an angular velocity graph. Okay? Omega is the slope of a theta versus t graph. Okay? And you can go backwards too. I mean, I'm gonna stop because I just keep repeating myself here. But yeah, there's so much translation between the two things. So I think I want to do an example now. Let's do it. All right, here we go. So in the first example, it's going to be a really simple kinematic problem. Now, I will admit that the kinematic problems in rotation are slightly more complicated because you have a few extra equations that you need to evoke when you do this stuff. So we have a 5-meter diameter merry-go-round. It's turning with a period of 4 seconds. It slows down and comes to a stop in 20 seconds. So for the first part, we want to know what the speed of the child is on the rim. Now, for part A, just to be clear, part A is initially referring to uniform circular motion. Okay? That's what's happening in part A. We haven't slowed down yet. Not yet. And so the equation that we can use for velocity, and there's a lot of equations that may come up, but the one that makes the most sense is 2 pi r, which is the circumference of the circle you travel in, divided by the time. So it's just distance over time. That's it. So we got 2 pi. The radius is 2.5. And let me tell you something here. This is going to be a very annoying yet common theme in these problems. We will always give you the diameter. Always. I don't know why. I'm sorry. It's just a thing. You're always given diameter. You got to make sure you convert it to a radius. Will you do it? Probably not. But at least I'm warning you. Maybe you will. Okay. I don't know why this is a thing. It's so obnoxious. But anyway. 2.5. Of course, your period is 4, not 20, because 20 is when we are slowing down. So I get a speed of 3.9 when I round it. It's actually 3.925, but I rounded it because I'm presenting it as an answer. All right. How many revolutions does the merry-go-round make as it stops? Right. There's a lot of steps here. Now, I will tell you this from the start. When you read this question, the first thing that will come to your mind is, I need to use this equation right here. That is what I call the second equation of kinematics. And you're basically solving for omega final. That would give you the angular displacement, which is equivalent to determining what the revolutions are. Okay? All right. But in order to do that, I need several details. As you can see here, I need to know what the initial value of omega is. I need to know what the value of alpha is. So I'm going to take a step back and do 2 steps here. I'm going to work out what omega initial is. And the equation for that is to take the velocity and divide it by r. I work the velocity out in part A. I divide it by my radius. and I get 1.57 radians per second. Hey, stop having fun. I'm working. I'm just kidding. All right. My kids are having too much fun. It's just, no, I'm just joking around. It's fine. All right. 1.57. You know what? I know what 1.57 is. That's pi over 2, isn't it? I think it is. It is pi over 2. All right. Useless detail. I need to know what alpha is. The definition of alpha is delta omega over delta t. That would be omega final minus omega initial. Omega final is 0. We come to a stop. Omega initial, I worked that out in the previous step. 1.57 divided by 20. And I end up with this. Oh, I did that wrong. Oh my goodness. Sorry. Ooh, bad. Sorry. Okay, I'll fix this in my slides later, but that's not meters. It is not meters. What is it? It is radians per second squared. I'm very sorry about that. I had to cook this up right before lecture, and I was really pressed on time here. Sorry, that's not meters. That would be what the acceleration is, but that's not what we're working out here. We're working out the angular acceleration, and so that's actually in radians per second squared. My apologies. You can make fun of me later. Now I have everything I need for the equation. The initial position, I'm just going to say 0. And the rest of the values are in here. And I work out 15.7. Now this equation, if you do things right, which you should be doing everything in radians, will give you radians. But we don't want radians because the question asks specifically for revolutions. So you will divide your radians by 2 pi, and it rounds to 2.5 revolutions. So this merry-go-round that's initially spinning with a period of 2, sorry, if it stops in 20 seconds, it will rotate 2.5 times before it comes to a stop. So, see this slide? You should print this out. You should frame it. Put it in your bathroom or something so you can see it every single time, and you'll learn the stuff. But this is the essentials of rotational motion. What is this? This is redundant. Redundancy? Hold on. Oh, I messed this up. Look at that. Sorry. You already know the answer here. Oh, wait. What did I do? Oh, it's the opposite question. Oh, I'm dumb. Okay, sorry. You saw this question. And this question is speeding up instead of slowing down. Okay, this is speeding up. And so a speeding up means the omega and the alpha are the same. And since we're going clockwise, omega is negative, therefore alpha is negative. All right, that's a terrible question. I probably will delete that one, actually. All right, so one more angular kinematic question before we can move on from this and start getting into the details of rotation. Let me bring up my... All right, so in this example here, we have a car engine, and the crankshaft is idling at 500 RPMs. I guess we're at a intersection. Light turns green. Hit the gas. The crankshaft rotation. Now these are omegas, just to be clear. Radians, not radians. Revolutions per minute are radians. We increase our angular velocity of the crankshaft to 2,500 RPMs over the course of 3 seconds. So that's a change in the angular velocity, which means there's an alpha. And we would like to know how many revolutions does the crankshaft make in 3 seconds. So unfortunately, this is another terrible aspect of these problems. We're always going to give you RPMs, but it's really not appropriate to use RPMs in your kinematic equations. Again, rather obnoxious, apologies. But you will first need to convert the RPMs to radians per second. And the way that you do that is you can multiply your RPMs by 2 pi over 60. And that converts it to radians. Now I left it as a multiple of pi because eventually the pi will cancel out. That's why I did that. So it's 50 pi over 3 radians per second. I'm going to leave it like that. You want to do the same with the final angular momentum. It's going to be 250 pi over 3 radians per second. And now we want to calculate what the angular acceleration is. So we subtract the final minus the initial divided by the period of time. I happen to get 200 pi over 9 radians per second. And now we can jump into the same equation that you saw before, which is this thing right here. I plug in my values. I have a 0 for the initial position. I have my initial omega times the time. I have my angular acceleration, which is positive because we're speeding up, times the time squared. And what I end up with is 150 pi radians. I'll need to convert that into revolutions. This problem seems to be awfully redundant from what I did before. Maybe I don't even need this problem in here. But that's what we're looking to do there. All right. I want to be done with this. Let's move on to the good stuff. Ooh, that's not what we want. Not yet, at least. Okay. So, now, that was meant to be sort of a review of rotational motion in addition to introducing some rotational kinematics. So, now if we go back and think about particle model, okay, particle model. What is the particle? That's the thing. If you have an object with size and shape, you know, one fair question is how do you decide on what the particle is? Is it the middle of the object? No. No. It ends up being the center of mass of the object. Now, why do we want to choose the center of mass? Because you think it might make sense to say, well, let's just choose the spatial center of the object. That might make sense. But there's a very important principle at work here. If you take an object, okay, like say for example you have this triangle here, right? And say it rests on ice so that you effectively have no friction. And you kick it, right? It's going to start to spin. But what is the axis of rotation? Well, it turns out that the location of the center of mass is the axis of rotation for the spinning object. And that's why it becomes appropriate to use it for our particle model. Okay? Now that creates a problem for us. When we want to convert our problems to the particle model, we will need to figure out what the center of mass of our object is. So that's the next step. That's what we're going to look into now. How do you calculate center of mass? Okay. Oh, I got a question here, I guess. All right. Baseball bat is cut in half. Oh, baseball. Oh my gosh, I miss baseball so much. Big baseball fan myself. All right, baseball bat is cut in half at its center of mass. Which end is heavier? So you see the center of mass at the top there. We want to consider which end is heavier. Not an entirely complicated problem. So you can probably see right away that the answer here is C. The two ends weigh the same, which is basically what the meaning of center of mass is. Center of mass is literally that. That means when you have the center of mass, you have exactly half of the mass of the object on one side and half on the other side. So as far as gravitational attraction is concerned, it's equal on either sides. If I had that bat with me and I put my finger directly underneath the center of mass, it would be balanced. Just like I could take my calculator here, and it's not uniformly distributed, but apparently the center of mass is located right above my finger because the object is not experiencing any kind of gravitational torque, which means there's no side of the calculator that experiences a greater force than the other side. And that is apparently what appears to be true here. What else do I have here? Does this even work? Oh, this is too awkward. Ugh. Well, the center of mass of this object, oh my goodness, it's so sensitive. It's somewhere around here, apparently. Somewhere there. Okay, I can't do that. I'm not going to break glass right now. Ugh. All right, so when we do center of mass problems, there are two different scenarios we're going to consider. There is what we call discrete distributions of mass, and there are continuous distributions of mass. I will first talk about the discrete versions. So the discrete versions, what does it mean? What do we mean by discrete? What we mean by discrete is this. We can take our masses and turn them into points, and then we can simply create a weighted average of our points. Okay, weighted average means weighted in terms of mass. So for every single point that we want to consider, we can multiply that point by its mass, add it all up, and divide by the total mass of our system. And that, by definition, by the way, if you look over here, these summations that you see here, this is the definition of what we call a weighted average. Okay? So if, for example, one side of an object contains a lot more mass than the other side, you would expect the center of mass to be skewed towards that side. That's what we mean by weighted average. Okay? All right. So these problems are very easy to solve, fortunately. Okay, so let's look at the discrete first before we get into the continuous. And I think I have a problem. I better have a problem here. I better. Oh, look at this. Okay, so we would like to determine what the center of mass of this discrete distribution of mass is. So it's discrete because we can treat these three objects as if they are point sources. They are connected by these rods. The rods, however, are massless. So we will assume that the rods are completely rigid. They can connect our objects up, but they don't contribute to the center of mass of the system. They just allow things to be connected and to move together. That's the idea. So let's look at this problem. All right. So there's actually two different parts to the problem. We first want to find the center of mass, and then we want to figure out the second part of the problem, which is having us figure out the speed of one of the objects. Okay? So the definition, and what you see on the left here, is what the definition of center of mass for discrete objects are. Right here. That's the center. That's the definition of the center of mass. So for every mass, and we have three of them, we are going to work out what the product of their x positions times their masses are. Now, I've decided that I'm going to create a coordinate system that is centered at mass A. So that means mass A has a position of 0, and so does mass B. They are located on the y-axis, so their x-coordinate is 0. Mass C, however, is 10 centimeters to the right, and so I will put that in here. Now notice I did something that I don't normally recommend you do. I did not convert to SI units. And the reason why is because we have ratios here. And you can get by with non-SI units. There are no constants here. Everything's ratios, so you can use grams, and you can use centimeters. That is acceptable here. So anyway, when I evaluate this, the total mass of the system is 600. So it's basically 300 over 600 times 10. That could be 5 centimeters, which, as you can see, I've already identified where this is located. The center of mass, as far as X is concerned, is in between A and B and C. Then I switch to Y. So obviously the position of particle A is at 0. The 20 gram mass is up here at 10 centimeters. And the 30 gram mass is on the x-axis, so it has a y coordinate of 0. And then effectively, I'm looking at this ratio, 200 over 600 times 10. That's a 1/3 times 10, 3.3 centimeters. And so that's what I've plotted here. In terms of x, I'm in the middle between A and C. In terms of y, I'm closer to A than I am to B. If you see here, you have 400 grams on the bottom and 200 grams on the top. So it makes sense that our center of mass is skewed downward. It's not in the middle. It's not the spatial center. It's skewed downward. And so we end up with a center of mass that is 5, 3.3 centimeters. Okay. Now I want to find the speed of the 200 gram ball if the system rotates with a period of 7 seconds. Okay, so that means I will need to know a distance. In order to calculate this, okay, so everything's going to rotate about this point right here. This is the center of mass. And that means B is going to move in a giant circle. Let me try to draw that circle for you so you can see that. I'm not going to do a good job of this, I guarantee you. I'm going to try, though. Oh, that's so bad. Ugh. What am I doing? Let me try that again. I think I have to start. I know what I got to do. I got to start in the middle. Oh my goodness. Okay, I'm going to try one more time and I'm going to give up. I think I got to start here and go out like that. Oh, that is so bad. Oh. Does that work? Don't make fun of me. That's kind of good. Look at that. That's pretty good. Yeah, that circle is probably pretty accurate, honestly. So B's going to move in this big circle here. I think I did a good job this time. And I want to know what's its speed if the ball rotates with a period of 0.7 seconds. Well, what do? Well, I have to figure out omega. So 2 pi over 0.7, which is the period, is 20 pi over 7 radians per second. I convert that to a velocity. That's the equation to convert an angular velocity to a linear velocity, and we get 75 centimeters per second. So, whatever the distance is here, this object moves around at 75 centimeters per second. That's a great problem. That's a fantastic problem, actually. So, yeah, we worked out center of mass, and then we decide to apply a little bit of kinematics, just a little bit, not too much. Let's get back to our lecture. All right, now, what if you don't have discrete distributions of mass? What if you have continuous distributions of mass? Well, I mean, if you remember, or you're starting to get into integral calculus, when you take limits of summations, they turn into integrals. And so that's what we are doing with the equation that you see here. We take the limit that the masses go down to an infinitesimally small size, and then we try to work out how to add up all those little pieces. And so the discrete distribution turns into a continuous distribution if you take limits, and those limits then will turn these expressions into integrals. And this is, I mean, I will be honest here, this is very challenging. It's something that I would like to really introduce now, because if your plan is to take 120, you will see integration a lot more. We really haven't done any proper integration in the course yet, mostly because I understand that in Math 150, you don't really cover integration until the end of the semester. So I think some of you are probably just getting into that now. So I'm not going to have any, major expectations of you. In fact, I'm really not going to require you to be able to perform any integrations. In 120, that will not be the case. In 120, I'm going to mentally torture you with integration, which you will probably like when it's all said and done, because it's a lot of fun, to be honest. Okay, but I'm going to show you at least one example of this. And again, I'm not going to require you to perform this, but it's very important that you see one particular integration to understand what to expect later. Okay. Now, when you do these problems, one of the keys on these things is to try to understand, what is dm? It seems very strange. What is dm? Let's look at that. Here's dm. Okay. I'm going to do an extremely simple example. About as simple as I could possibly make it. Okay. I want to know what the center of mass of this one-dimensional rod is. The rod has a mass m, which is uniformly distributed across the entire rod. Okay, now all of you know the answer to this. You already know the answer. The answer is the center of mass is in the middle. That's the concepts. You understand the conceptual side of this. However, it would be nice to see how you mathematically figure this out. Okay? So let's see how you mathematically prove this. Here we go. So here is my definition of center of mass for a continuous distribution right there. Okay? That's how we start. Now, in order to figure out my dm is this. This is what it means. You're trying to select tiny pieces of mass. You're trying to specify where they're located. And you're working out the summation of all of the little masses over the distance that they apply. Now, to do this, you will have to invoke this concept called linear mass density. Linear mass density. Okay? And we indicate that with this Greek letter lambda. You will see a lot of lambdas. Lambda is a ratio of mass over distance. But because it is a density, it doesn't care about how big or how small something is. So I can make a ratio that is the mass of the object divided by, I can make a ratio that is the entire mass of the object divided by the entire length of the object. That will define for me a density. But I can also say I can have an infinitesimally small mass. So you can see in the picture down here, I have a little dm. It's a little tiny bit of mass. And it exists over a little tiny section of the rod. And because it's density, these two things are equal to each other. So I solve for dm, which you see down here, and I plug that in to the equation that's up here. Right there. So instead of dm, I now have lambda dx. And lambda is a constant. It comes outside of the integral. I'm integrating my function from 0 to L, from here all the way over to here. So that's a simple power rule for derivatives. So if it's x, you add 1 to the exponent, you divide by that number, so I get 1/2 L squared. I put in my limits and end up with lambda m times 1/2 L squared. I can substitute for what lambda is. Lambda is m over L. So if I do m over L here, the m's cancel out, one of the l's cancel out, and we get the familiar expression. Oh, that's not what I want. We get the familiar expression that the center of mass is exactly half of the length. Now, we already knew this. All of you knew what the center of mass of the uniformly distributed rod. but this is the mathematics behind it. This is how we prove it mathematically. And I will recommend to you to spend a lot of time looking at this example and trying to understand what's going on here. And one of the things that is going on is this. You are building an integral, okay? Now, unfortunately, when you take all your math courses, they don't teach you this skill, which is very unfortunate. What they teach you in math is how to evaluate an integral, but they don't teach you how to build an integral. For example, if you've taken enough integral calculus, you may be familiar with what's known as the shell method. But the vast majority of instructors that teach shell method simply provide you an equation that you analyze. But that equation ultimately comes from you trying to build an integral. You try to imagine a shape, you cause a rotation about an axis, and it allows you to build the integral. Except they don't teach you how to build the integral, they just tell you how to just plug things into a function, and then you learn how to evaluate the integral. Which is unfortunate because evaluating integrals is a trivial, mindless task. I mean, you can plug integrals into a calculator. You can go to Wolfram Alpha, and you can evaluate anything you want. So, not a useful skill, honestly, when a computer can do it for you in a few seconds. What you don't learn, unfortunately, is the process of building integrals. And I'm going to teach you a little bit about that today, and if you take 120 with me, we're going to do that a lot. You're going to learn how to build them. And building is more important than evaluation. Way more important. Okay. Moving on here. So in my next example here, this is another, how do we build the integral? Okay. So, we have a triangle. Now, earlier on in the lecture, I sort of talked a little bit about triangles, but determining the center of mass of a triangle is not obvious. There really isn't an intuitive way to know what the center of mass of the triangle is. We do know, however, it's not the spatial center of the triangle. The spatial center of the triangle would be an axis that goes right down its center and would be located at basically 15 centimeters according to the figure here. But that's wrong. You know that's wrong because there's more mass on the right than on the left. So we actually need to figure out what the center of mass will be. Now, there is some symmetry in the problem here. So the way I drew my triangle is there's equal mass above and below the x-axis. And so what that tells us is there's an immediate result we get from this, that the center of mass of the triangle is located on the x-axis. That's clear. We can tell, however, though, from this figure that the x-coordinate of the center of mass is going to be skewed towards the right-hand side. So it's definitely not at 15. We know that the center of mass of this triangle on the x-axis is somewhere past 15 centimeters. But where is it? Well, that's why we do the integration. So we start with our definition of the center of mass. That's our definition. Now, these problems will typically involve 3 steps. 3. And the 3 steps are this. What is dm? What is x? What are the limits of integration? Okay. Now I drew this figure in a particular way so that I oriented it, I should say, so that it's easier to do the integration. Okay. Now the trickiest thing about this is try to determine what dm is. And so the question is this: how do you break up the triangle into pieces that you can add up? That's really the question. And that's what dm is all about. dm is, what are the infinitesimally small pieces that I break my triangle up into to add them up? Well, those pieces are basically little rectangles. I mean, if you want to be super technical, you actually might want to call them trapezoids. But there's a dx here, so I'm going to say rectangles just because I don't want to be philosophical about my differentials here. But just imagine that you break this thing up into tons and tons and tons of rectangles. That's the key. Every rectangle has a thickness dx and a height that is 2/3 x. Okay, now this line here has a slope to it. Okay, we go 30 centimeters to the right, we go 10 centimeters up. That means it has a 1/3 slope on it. So that means we're 1/3 up and 1/3 down. That means the entire extent of the rectangle is 2/3 x. So I have defined here a surface mass density. So this is, we did linear mass density, which is lambda. Surface mass density is going to be this symbol sigma here. And it's defined as mass over area. So the entire mass is m. The area of the figure is simply the area of a triangle, 1/2 base times height. And the meaning behind the density is that you can also equate this to a dm over dA. So I'm going to solve for dm. It's sigma dA. Sigma is basically this thing right here. dA is a differential area. So that's going to be a rectangle's area, right? So it's going to be the height, which is 2 times 1/3 x. That's the height of the rectangle. And the thickness is dx. So I have this expression here that represents how I figure out my dm's. And notice there's a variable here, x. So that means the further you get to the right, the more mass your little pieces have. And I'm going to plug that in to the expression that's over here. So this gets plugged in right there. So my dm turns into 2/3 sigma x dx. That's great. Now my x, I don't have to do anything with my x. X is just how I select my dm's. So I could select dm's anywhere between 0 and 30. But it's simply a matter of how far to the right I am, which is just the x-coordinate. And of course the limits of integration are 0 to 30, which because I'm selecting dm's from 0 to 30. And so now you've done it. Now you've built it. This is the built integration right here. The second line is your built integral. And this is where mathematics says, okay, now I'm going to teach you how to do this. Okay, mathematics unfortunately does not tell you how to go. I mean, depending on who you have, I suppose, but most mathematics doesn't say, hey, how do you go from here down to there? Well, most math classes won't tell you that, which is a little sad. The math classes will tell you how to get from here down to here. And so I'm not going to go over the mathematical steps exactly, but it's simple power law stuff. You get an x squared, turns into an x cubed over 3, yada, 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 20 centimeters. Okay, so the center of mass is apparently, of course, we knew it was skewed to the right, but at least to me, I don't know. I don't think it's obvious that it's 20 centimeters. It's exactly 2/3 in. To me, that's not obvious, but that's what it turned out to be. So, fantastic example. I recommend that when I post my video lecture, you go back and you watch it 20 times for 20 centimeters. No, don't do that. Well, you can do whatever you want. It's quarantine. You have all the time in the world, right? All right. Really great problem. Good example to learn. It's fantastic in a million ways. All right. So now that we have this tool at our disposal, we know how to calculate the center of mass. So now we can start to do some interesting things. Let's start to explore the other aspects of physics that we already know. How do we characterize the kinetic energy of a rotational object? Okay, so what you know already is this, 1/2 mv squared. If you throw an object through the air, right, the kinetic energy is 1/2 mv squared. But what if the object rotates? I mean, that's motion still, right? So how would you characterize its kinetic energy purely based on rotation? Well, we're still going to use, our familiar 1/2 mv squared. But what does m and what does v mean? Well, if you have a continuous object, you're going to have to break the object into pieces. And you'll have to consider how each piece moves about the axis, which honestly, it seems really hard. I mean, if you look at the example I have in the upper right here, I've identified 3 different locations, and I can say, well, let's say there's a certain mass located here, and let's say because of the rotation it moves with a certain velocity. And we already know that if the velocity is closer in, it's slower, and if it's farther away, it's faster. But it just seems so sloppy to do this. It seems so difficult to try to break the thing up into pieces. So we're not going to do that. In fact, what we're going to do is we're going to change our familiar 1/2 mv squared into our rotational equivalent. And we do that by changing all the velocities into radius times omega. So that means every place where we're considering mass, we're only really considering how far away the mass is from the center. So all the v's turn into all the v squares, I should say, turn into r square omega squares. Okay, well, omega is constant. It's constant throughout the entire object. So it's not part of the summation. If you want to select lots of pieces, you can take them all out. You can take the omegas out of all of them. And you end up with this expression down here, which is a really interesting expression. Here's what the expression says. Ooh. What's going on here? All right, so the only part of it that really cares about the mass of things is this thing in parentheses here. Okay, right here. And what this thing is here, this is a really interesting expression here because it's basically a statement that says, where are all the masses located? That's it. That's what it says. Where are all the masses located? But that thing I just boxed there has nothing to do with the motion of the object. There's no v, there's no omega in the summation. And so what that says to us is that all objects with shape and size have an inherent distribution of mass that is independent of its motion. And so in physics, we recognize that principle, and we have a name for it. And that name is called the moment of inertia. The moment of inertia is basically the rotational equivalent of mass. Rotational equivalent of mass. And it's something you can characterize for an object of any size or shape, regardless of whether it moves or not. And so that means the expression that I showed you in the last slide can be simplified to this statement right here, which is saying that the rotational kinetic energy of the object is based on its moment of inertia times omega squared. Now, omega squared is uniform throughout the object. I, however, needs to be worked out. So the rotational kinetic energy of an object is actually very simple to do, but it does require you to take a first step. And the first step is to figure out what I is. And that's really what the rest of the lecture is all about, is how do you figure out this I here, okay? And now, what does this mean? What does this I mean? Well, here's what it means. Say you have an object where you have say it's a uniform disk. Uniform disk, right? Do I have a uniform disk around here? I don't think I have a uniform disk anywhere here. I can't see a disk. Anyway, say you have a uniform disk, right? There's mass distributed all throughout. There's some near the center. There's some near further out. The stuff that's further out will create a larger moment of inertia. What you're saying is this: if your mass is distributed very far away from the center, it's harder to make the object rotate. Okay, so if you have like a tire, for example, a tire has a hole in the middle. All the mass is distributed on the outer edge of it. So it's harder to rotate a tire than it would be, for example, a disk that has the exact same mass. Because with all the mass further out, it's just going to be harder to get it to move because you're going to have to raise it to some speed, and it's just harder. It's just basic inertia. So this I here, which is what we call the rotational equivalent of mass, really cares about where the mass is. That's why you see an r squared here. It really cares about where the mass is. And the farther it is away from the center of the object, the more challenging it is going to be to make that object move. Okay, that's the interpretation. That's what you should get out of that. Okay. Now, moment of inertia is going to seem a lot like center of mass problems. There's one major difference, though. Moment of inertia definitely needs a axis of rotation. Now, the center of mass of an object is a intrinsic axis of rotation. So if you're not told an axis of rotation, you will assume the center of mass. So let me reiterate what I'm saying there. Say you're asked to find the moment of inertia of an object, but they do not specify what the axis of rotation is. You would have to assume it's the center of mass because that is the natural axis of rotation. So you have a separate problem where you have to work out the center of mass, and then you can work out moment of inertia. Fortunately, in this example here, we are told what the axis of rotation is. It's not the center of mass. It happens to go through A. So it's an axis of rotation that kind of comes in and out of the page. And so what happens is this object would rotate about that center of mass. It means the whole object is going to rotate sort of like this as it goes. And the axis of rotation is at A here. So what you'll need to do is you'll need to evaluate this summation here. You have to take every mass and multiply it by how far away it is from the axis of rotation. Now for A is on the axis of rotation. So the R is 0. The 200-gram mass, however, is 10 centimeters up. So I'm going to, now, these are not vectors. You don't care if you're up, right, doesn't matter. It's just distance. No vectors here. 0.2 times 0.1. Okay, the 300-gram mass is to the right, 10 centimeters, so 0.3 times 0.1. You evaluate all this stuff and you get 0.05 kilogram meter squared, which is our units for moment of inertia. Okay, notice something I did here though. I use SI units. The reason why is because we are eventually going to use this to work out torque, which is in the next lecture. But torques require SI units. It's not like center of mass. You've got to do SI for moment of inertia. I can emphasize that more. Okay. All right. So the previous example was discrete moments of inertia. Well, the same thing applies here. What if you don't have discrete masses? When you generally don't have discrete masses, you have continuous masses. And so what if we have a continuous mass? Well, just like before, your summation as the limit that the mass drops to 0 turns into an integration. So you'll have to evaluate this integral here. Now, most of the stuff that I talked about in our center of mass integrals will apply here. You have to figure out a dm. You have to figure out how far away your dm's are from the axis of rotation. That's what r is. And then you got to figure out your limits of integration. So it's done in pretty much the same manner. Okay. So let's look at an example of that. All right. So I've got a few more examples here. All right. So we want to calculate by direct integration the moment of inertia for a thing of mass m and length L. About an axis located at distance d from one end. All right, so let's bring up the example here so you can see how this is going to look. Ooh, where's that? Here it is. Okay. All right, so now moment of inertia for a thin rod of mass L, a mass M, length L, about an axis located distance d from one end. So if you look at the picture here, I have my rod of length L. I put a coordinate system down that is exactly a distance d from one end. So basically what I'm figuring out here is I'm figuring out how to calculate my moment of inertia for pretty much any location I want to consider. Now, of course, the center of mass is in the middle here, okay? But I'm choosing it to be at one end because I'm going to do this problem in a much more grander way. So here's what you do. All right, here's what you do. You start with the definition. You start here. The moment of inertia is the integral of r squared times dm. The next step is, what is dm? Well, we're still using linear stuff. Lambda, mass over length, dm over dx. Simple enough. I substitute that in here instead of dm, as you can see here. Instead of dm, we have lambda dx. How do I figure out where my dm's are? Well, everything's along the x-axis. I'm not going up or down or anywhere else. So my r is simply x. And what are my limits of integration? What is the range of values where I select my dm's? Well, they could be all the way on the left, which would be minus, not that. Let's get rid of that. So it's a range of values, right? And the range of values are, it could be all the way on the left, which is negative d, or it could be all the way on the right, which would be the length of the rod minus d. And that's the full range of values where my dm's will exist. So they all get plugged into this equation down here. Okay? The physics is, it's a bunch of math now. Okay? So what do I got here? Well, I integrate my x squared. That's 1/3 x cubed. Lambda is a constant. It comes out. I evaluate my limits. And I end up with this expression that tells me what the moment of inertia of the rod is at any distance I select. Well, what's one distance that would be interesting? Well, if you look at the bottom here, calculate the kinetic energy of a rod that rotates with a period of blank about a pivot that's through one end of the rod. So if it's a pivot's through one end of the rod, I'm supposed to do that. Okay, that could be on the left or it could be on the right. Let's just say it's on the left here. That would mean d is 0. So if I take this equation right here and I plug in d of 0, I get 1/3 ml squared. That would be the moment of inertia of the rod through one end. And then if I want to determine the kinetic energy, you already know what that is. It's 1/2 I omega squared. I know I now, 1/3 ml squared. What's omega? Omega is going to be given by 2 pi over the period. Period's 1 second. Omega is 2 pi. I plug all that in. I clean it up, and I get this nice expression here, which is the kinetic energy of that rod. Okay. Fantastic. Now, this table I have here is a pretty standard table. You're going to find this in your textbook. You can find this anywhere online. I happen to be using this from a textbook I used a few years ago, but the information has never changed. It's the same stuff. So here's the equation that we already worked out. We worked out this right now. Now, how would you work out this one right here? 1/12 ml squared. Well, guess what? You go into your equation that I just derived there, and your value for d is now L over 2. So if you want to know the moment of inertia through the center, make d equal L over 2, simplify, you will end up with this expression here. Now, what's the difference between these two expressions? Well, apparently, if you take the moment of inertia through one end, you have 4 times the moment of inertia. That makes sense because if you have the rod in the middle, you have equal mass on either sides. So it's easier to rotate. But if you have it through one end, then you have some mass that is actually pretty far away from the axis of rotation. And the farther away mass is from the axis of rotation, the harder it is to move it. It turns out to be a factor of 4. It's because of the L squared. But we have different configurations here. We have the slabs. You can see how that works. We have a disc or a hoop. You can see how that is. We have spheres, solid, or hollow. And so what you'll need to be aware of is when you solve your problems, you need to be sort of aware of what shapes you're dealing with, and that allows you to know what you're going to work with here. Okay. Clear. Moving on. All right. I already said this. Nothing new here. So this question here, you should look over this question. Again, I want to get through this here, so I'm mostly devoting this toward the video. If you're watching this as a video, just pause and ponder and ponder and ponder. The answer here is going to be B. Okay. Why? Well, the moment of inertia equation is 1/2 mr squared. Now, r squared means that r is a more sensitive parameter than m. So if you drop the mass by a factor of 2, but you increase the distance, that's more important. You're basically saying that you have mass distributed much farther away, and that becomes harder to rotate. In fact, the moment of inertia for B is exactly double for A. So if you say you impart a bunch of kinetic energy, the same amount of kinetic energy is only going to make B rotate half as quickly than A. Because, again, you're distributing the mass so much farther away. That's the idea. Now, the last topic here is something called the parallel axis theorem, which explains basically how you could work out what the moment of inertia is if you happen to know what it is through the center of mass. Okay, and this is a little bit of a trick that just simplifies the mathematics of a lot of problems. And the best way I can illustrate this is if we go back to the table here. Okay, so this picture that's up top here. Okay, this is the moment of inertia through the object's center of mass. It's through the middle. Now I can use the parallel axis theorem to figure out this one without actually going through the integration. Okay, and here's what the formula looks like. It's the moment of inertia is whatever the moment of inertia is through the center of mass plus an mr squared. M is the total mass of the object, and r is how far away you are from the center of mass. So in this context, it would be this. Now the moment of inertia through the center of mass is 1/12 m. L squared, right? We're using L squared. So I'll do L squared. Oops. Plus mr squared. Well, m is m. But r, in this case, is going to be L over 2 quantity squared. That's how far we are from the center of mass. If we're on the edge, we're L over 2 away from that. Well, let's do the math here. 1/12 m if we square this, we get L squared divided by, what, 4 here? Okay, so what is 1/12 plus 1/4? Well, it's 1/3. So we end up with a 1/3 m L squared, which is what the result is here. So it's a little bit of the parallel axis theorem is a convenience. If you happen to know what an object's center of mass moment of inertia is, and you know that your axis is parallel to it, but just off to the side, you just got to work out what the mr squared is. So that makes the work a bit easier. All right, I am done. This took a long time, but it was fun. So